So this is the title page, and here you see the basic outline of my talk today. So two methods to look on that issue. Now about motivation. Why do we look on storage and solar? But we know that the physical problem, of course, the physical question about the mismatch of solar and demand, where we may need to store it. But there's also very important background trends that we have in the market. The price of solar and the price of storage have declined very much over the years, and we still see that there's a positive price trend, which means that these technologies are approaching, actually have already approached the market breakthrough. So combining solar and storage becomes much more motivated because of the price, which becomes now viable for the markets. And indeed, if you look on the recent scenarios that we have on the energy development worldwide and in Europe, you see that solar is really becoming dominant by the middle of this century. And just recently, the International Energy Agency, IEA, stated that solar may be now the new king in energy, based on its very positive development. So we will see much solar in the future, and that also emphasizes the need of storage. Now, that's emphasis comes to the fact that when you have much variable renewable electricity, solar and wind, that will require more flexibility of our energy systems and about our power system. And we're already now approaching in some countries critical levels of variable renewables, like in Denmark, Ireland, many other countries, which starts to emphasize the question of storage. So that as a background, let's go to the fundamental questions that we will discuss today. And the fundamental question is the optimal sizing of PV and storage. The system that we're looking on is very simple, and basically a solar PV storage system is simple. You have the solar panels and you have the storage, and so these are the two key components. You may have sometimes different balance of systems approaches, but the fundamentals is really always going to the PV and to the storage. Much of the analysis which I will show you and about those methods are based on a paper that I wrote some years ago. So I'm drawing some information from my earlier paper and applying it here today. So let's start with the storage problem in solar. And so, but even though I focus today on solar PV, which is the growing market segment of solar, the question of storage is a fundamental to any application of solar energy, being that the solar thermal system, being a remote power system in particular, or in the future, maybe solar hydrogen systems. You always need to look on the storage system. The storage problem is present in all applications of storage. The storage itself is an important component then in such systems for matching, typically matching the solar and the load. And there's a range of fundamental, let's say, science behind that. Matching against the second law of thermodynamics in a thermal system. We need to match voltage in solar systems and chemical potentials, etc. So the storage has also functional matching, which we wouldn't look much more on that today, but keep in mind that has a very important function also for the operational security of solar PV systems. At the very end, it always goes back, the sizing question goes back to the interplay of three components. That's the solar and storage and load. So those three components, they play together. How they match together will influence the size of the storage and the PV. So these three components, that's what we need to keep in mind now in the next slides when we look on the sizing. So before going more in details of the sizing principles, we need some metrics here to help us to value the storage. And one important parameter which we very often use in this context is the self-consumption or self-use of solar, which is defined as the amount of solar that we can use directly without any storage, plus the contribution which comes from the storage, divided then by the total demand. And typically we strive for as high self-consumption as possible. Of course, you have to do now optimal sizing that you don't waste too much solar in this process. But self-consumption is important. That's also a parameter that in some way tells which kind of interaction our solar system would have with the remaining power systems. So the basic goal is to maximize self-consumption. Now be careful also not to mix this with the solar fraction, which is very often defined as the fraction of all solar produced of the total load. So here we look on the useful side, the useful amount of solar that we can use. And we're using storage to extend that. When we do optimization, there's different principles for optimization, and you can optimize against different parameters. You can do technical optimization, economic one, perhaps operational optimization, or look on the environmental impacts. Now here we will look on the two first ones, on technical and economic one. And in case of technical optimization, and now relating to the self-consumption and self-use, we'll look on those regimes where we get the largest benefit from the storage. So we've tried to find some kind of a generic performance curves, which shows us where the benefits would be at highest. The second method is then when we think about economics of this solar PV, relates very often to finding the cost optimal, the minimum costs. And that would be a typical minimization problem, to find the minimum cost point against a certain parameter. And that would be a very traditional way of doing. I will do the economic optimization in a non-traditional way, and in the sense that we will actually combine both technical and economic optimization in both cases. So in our approach, we take the technical optimization and economic optimization approach, and let's see how the outcomes may at the very end then differ when we use these two sizing rules. Now about the metrics, if you just look slightly more carefully about the metrics, which we will use in the next slides. So there's different ways to show the performance of a solar PV system vis-a-vis the storage size. On the left-hand side, is a traditional way of showing. We have a certain size of PV. Here is a very big PV system. It's close to 60 gigawatts. This is actually for one country. And what I do here is I then illustrate the self-consumption, which is the y-axis, as a function of the storage capacity, which is the x-axis. So you see that once by the way, observe this is a logarithmic scale. So once I start to increase the storage in this case, and I have actually sized my PV so that it could produce all the electricity in that country over the year. But there's a mismatch between load and supply. So without storage, I couldn't do it. So without storage, you see in this case, the self-use would be about 40–45% in that range. But increasing the storage gradually, you see the storage start to compensate for the mismatch between solar and between demand. So at some point with very large storage, you see I could produce 100% of the electricity in that country. The gradient is quite steep. You see here also very steep progress at some point in the storage need to get a requested solar share. Now, the same figure, I'm using the same figure in the next to show some other metrics. I could, of course, scale the figure on the left-hand side with the capacity. the PV capacity. Then I get the storage to PV capacity ratio, which is now the x-axis here. And you see the same behavior, but maybe you already start to see what kind of a capacity would be most beneficial in this case. And the last figure here on to the right-hand side is that I just turn the scales. The y-axis will now be the x-axis and vice versa. On the x-axis, you have the share of PV, self-use share of PV, of total load. And you see that this is like a hockey stick, almost constant, then it goes just very, very rapidly up. And you find it definitely by visually already that the optimum is before the curves start to be vertical. And this gives you already a simple sizing rule. But let's keep on the growing part and let's avoid this very vertical kind of points where the benefits would be quite small. Now, using this principle, I now highlight a few cases about how the sizing would affect, storage sizing would affect the solar system performance. And I take 3 climates, a low, medium, and high solar climates, so Finland, Italy, and Saudi Arabia. And let's see what we can learn from this kind of a technical performance simulation. What I do here is I use hourly simulations to generate curves for the self-use vis-a-vis the PV size. For case where we don't have any storage and a case where we have an optimal storage. So let's see how we interpret these figures. And I start with the one which is in the here in the left corner. And let's take the case where we wouldn't have any storage. And that's the dark blue curve here. You see at the very beginning, when I size my PV very small, I can use all the PV. So self-consumption is linear to a certain point. And once I increase the size even more and more, what happens is that I produce surplus. And you see in this case of Finland, we level out to around 30–40% self-consumption. So even though I would still increase the PV size, the mismatch is such one that puts a limitation on the self-use growth. Now, if I put storage, optimal storage size, so that I would always have an optimal amount of storage, the self-use vis-a-vis the PV would be a linear curve. There would be always enough storage to store each kilowatt hour of PV. And that brings to definitely to this light blue curve, which would be a linear curve. So you can use each kilowatt hour of solar that you can produce. And that means that your PV size, which is now in terms of the percent of yearly load, correlates directly with the self-use. Now, the amount of storage that I would need in this case is the red curve here. It's the red curve here. You see the red curve in which when you start to increase now the PV, and let's keep in mind this is now the case with storage, you see that even though I don't need to increase much the storage, and you see that that what happens is that the self-use would increase. So up to, in the Finnish case, up to maybe 50–60% self-use, the amount of storage I need is still modest. But about that, when I go to start to go to 60–70% here on the x-axis, you see that the storage size start to increase. And I need a huge storage, indeed, capacity to compensate for the seasonal variation. So this flat part here is actually the part which compensate for the daily diurnal fluctuation of solar, day-night cycle, which is very regular. I mean, the physics is there. There's no uncertainty about that. And then this racing part of the hockey stick here, that relates to the seasonal part. That's where I need to start to compensate for the seasonal variation, which is very huge. So my optimum, in a way, in technical terms, would be most likely before we enter the seasonal mode. Now, the same behavior we see for Italy, which is the next curve here, and also for Saudi Arabia. The only difference here in relation to the northern climate is that, well, you would have a higher self-consumption without storage. Italy and in Saudis, I would come to 45% self-use without storage. And you see also that the storage demand is smaller. Putting these three climates together, and that's the last curve here, you see that in all cases I can use very small storage to compensate for the diurnal daily cycle. But then again, in all cases, we need rather large storage to compensate for the season cycle, which then would bring us a higher self-consumption ratio. But there's a clear shift in the sense that the more north I would be, well, the smaller the self-consumption without storage and the higher storage demand to raise the self-use after that point. So investigating now slightly more the curves here, and I do some surgery. I think I take now here the Saudi case again, and take the curve from the previous figure, and look on the storage demand, and indeed I can distinguish here between short-term storage demand and the long-term demand. So the very flat curve is for short-term diurnal storage, and then the very steep curve would be, the red steep curve would be for long-term storage. Now, looking at the behavior of these curves, I actually observe that the storage capacity that I need for solar has a quadratic term of the self-use. So the higher self-use is that my storage demand goes quadratically. So in a way, why the storage increase in this way? Well, is because of the mismatch on a seasonal scale, which leads to this kind of observation that the storage capacity is a quadratic term, a quadratic of the self-use. That's why when you have small self-use values, we go for small ones, the storage capacity demand is very small. Now, drawing some conclusions from these figures, we see that when we are at self-use values of about 50 to 70%, our storage capacity demand is quite small, a few kilowatt hours per kilowatt of PV. Going into the next mode, which would be the seasonal size. In the northern climates, it would be 2 orders. Yes, ladies and gentlemen, 2 orders of magnitude higher. In the southern climate, it may be about 1 order of magnitude or so. So the step from diurnal cycle just to get those, let's say 20, 30% more solar, you pay a huge price in terms of storage. So most likely it would be optimal just to look on the diurnal cycle compensation, and that would be fine. Now taking a range of other climates, not just with these 3 cases, but let's take a range of climatic zones from really high north to low south. We'd see the same actually. Same features, and it really says that the main benefits from storage in solar comes with a size around a maximum few kilowatt hours per kilowatt peak of PV, and the self-use that we could in that case get would be in northern latitudes up to 70%, even here in Finland 70% with a small battery, and in the south we would be already close to 100%. So let me demonstrate this also for Finnish case. Finland is the worst case in a way. This is very high up north. And I take now a very accurate simulation with a battery, which is size 10 kilowatt hours. It's a small battery already. But this would be a PV system which would be able to produce, so the size of the PV is sized so that it could produce all the electricity of the household, which is about 3,000 kilowatt hours a year. Now, putting this small battery here, actually, I could increase the self-use ratio by a factor of 2, or actually slightly beyond. So without storage, this system could produce about 33% of its electricity for self-consumption. Rest would be surplus, which you need to feed into the grid. Put the small battery, you can increase it to 70%. So 70% over time, this system would provide 100% electricity for a household in Finland. You see these kind of self-sufficient points here in the pie. The blue lines here, the blue areas shows where we really can produce all the electricity by solar. Well, here again, the challenges in the Finnish case would be 3 challenges. It's the November, December, and January. That's the seasonal fluctuation, which we can't, of course, compensate with the diurnal storage. You would need 100 times larger storage to get even those months covered in this case, and that would not make a sense. Now let me then move to just the final example would be the cost optimization. And here I make two important observations to make the optimization. First is that I can produce these kind of ISO curves for the self-consumption. So let me take, for instance, the light blue curve here is a 95% self-consumption ISO curve. So you have PV size, storage size pairs, which kind of can satisfy this curve. So you can slightly decrease the PV area and then compensate it by increasing the storage area here. And you get these kind of ISO curves. So on this curve, and you see on X and Y axis, we have the storage capacity and the PV size. On this curve, the self-consumption is constant. Let's keep this in mind. And then let's look on the cost of such a system where we have PV and solar. The cost function is shown here in red. C tot is actually a linear function of the PV size, PV system size, the array size, and the volume size. So A is the size of the PV array, and V is the size of the storage. It's a linear function. Now, what is the cost optimum brings us to a very clever thing is that let's use my ISO curves here. So actually the cost optimum can be found in the point where this linear function touches the ISO curve, shown here in this picture now as the dot. That's the optimum point. I can do some mathematics that I can even analytically solve that point. It's a long story, but you can also do it graphically. So just fit the slope with that curve, and that's where we have the optimum point. So in the last figure that I have in my presentation, I updid that, and now what I get is let's say cost optimized PV array storage size curves. And what I have here now is on the y-axis, I have the optimal size of the storage now scaled to the PV size, and here on the x-axis I have the cost of the storage, again scaled to the PV unit cost. The curve to the right may be interesting. That's the range where we have the cost of PV and storage are today, but it shows an interesting thing is that actually relative-wise, storage would be much more valuable in south than it would be in the north. So why that? Because in north you need always more storage. The point is that in the south you have much more solar, and that would emphasize in a cost optimization the storage. Whereas in Finland we don't have so much solar. So I need to really have a large array to produce solar enough. So it's interesting that in the northern latitudes, actually my size, if I look on the ratio of PV to storage, I would have more PV in relation to the storage than in the south. And this in a way cost optimization emphasizes also the role of storage in the southern hemisphere for, of course, diurnal compensation of the solar. So with these words, ladies and gentlemen, I'm finished with my lecture. I thank you so much for your attention, and if we have time, we can maybe have some questions.
Thank you very much, Peter. Colleague, do you have any questions? Any questions? Zani, could you unmute everybody?
They should be able to unmute themselves, Safa.
You unmute yourself, ask questions if you have any question, please. Nothing? No questions?
I have a question.
Yeah, please go ahead.
Yeah, first of all, thank you for the very informative presentation, for the very informative lecture. I would like to know, from your experience, when comparing different locations such as Finland and Saudi Arabia, certainly the weather conditions will be different, and so it will have a different impact on the batteries that are being used or the storage system that is being used. And so when doing such comparisons, is the storage system kept constant or not? And with regards to the impact of the area, the prices of the area, so a meter square here is completely different than the price of a meter square in a different country. How to approach this situation?
Yeah, thank you very much. It's a very, very good question. And if I just relate your question to the last slide that we have here on the screen, it means that your point on the x-axis may change because of the costs. So on the x-axis, we have the ratio of the costs. But let's say that if you look on the difference in the sizing, and I'll keep in mind the sizing is storage volume divided by the PV size. It's a scaled storage. We see that in spite of the costs, it would mean that for each kilowatt of PV which you would have in the south, you would put actually more storage than I would do it here in the north, because you have so much solar. So in countries where I don't have much solar, I need to really put much larger array to get the solar than to the storage. So the fundamental conclusion in that sense, and I keep in mind that this is now scaled values, you would need less, of course, kilowatts or PV for the same load than you would need here. In absolute terms, you definitely, you may need less, but in a scale, relative terms, relating to the PV array you have, the south would kind of benefit of having slightly larger storage than we would have here in the north, where we will need always to put a large PV array because we have so little solar radiation. But again, you can move along the curve here to get the along the x-axis then to get the exact values for that.
Thanks, Peter. Thank you. So,
yes, can I have one question, please?
Yes, yeah.
Yes, Tony Marmont. Can I ask Professor Lund, if the system is connected to the grid and you get given during the midnight hours and high paid if you sell it in the daylight hours, this will affect the grid storage ratio battery if you can work that in. What do you think?
You're right, definitely. This is now a simplified case in a way, but if you would kind of link the grid, then you would look on the arbitrage possibility that you may have in storing and selling electricity. In this case, I think as a general rule, I would most likely slightly oversize the battery in order to enable this point here. But you're right, that would slightly more bring a new let's say variable into the picture, and in that sense you would need to optimize against the revenues that you might get from selling the electricity into the grid in this case. And I would imagine we would slightly increase the battery size in this case.
Thank you, Professor Lund. Yes, I have done that, not knowing what the correct thing to do, but you confirmed it. I've got a 0.85 megawatt solar panels, and I bought a 2 megawatt Tesla battery to optimize the income so that the income could go to a university doing Alzheimer's research.
Right. Yeah, I mean, as you did intuitively it correctly. Yes, yeah, absolutely. Even the numbers are very good in that sense. I congratulate you for invitation.
Oh, thank you.